All right, welcome everybody to Machine Learning 201. What we're going to do here, I'll put on PowerPoint in a second, but what we're going to do here is I used to have an hour-long class where I would teach neural networks and image recognition. That's sort of the problem that we're going to work on, but I expanded it to 2 hours to have it be hands-on. So in the past, I would just go through PowerPoint and I would talk for an hour, and people liked it. It's somewhat interesting, but I think it's even more interesting to kind of roll up your sleeves and actually train a machine learning model yourself. And that's what we're going to do with this class. So I am aided by Marta Manzin, who will teach some of it, and Melis Gokalp, who will teach some of it as well. Do you guys want to introduce yourselves? And Marta, you're on mute.
And I am muted. Can you hear me now?
Yes.
Great. Hi, my name is Marta. I am a developer in Hellshire. I've been with the company since 2020. And today I will take you through our deep learning module. And I will be available for any questions during the exercises.
And Melis?
Hi, everyone. My name is Melis, and I've been with data platforms for almost a year now, and I can help you with any questions you have. I really like deep learning, so ask me questions.
Great. Okay, so both of them, as you go through the exercises, lean on both of them with any questions or challenges you might have as you go through it. Okay, great. So again, we're going to do image recognition as kind of the use case. And deep learning is a particular kind of machine learning, which we'll describe in great length in this period. And that's been particularly effective at image recognition. So that's why the two are going together here. So let's first start with the problem that we're going to solve. And it is to recognize handwritten digits. Now, if you think of the traditional, first of all, you can think of this as a very useful problem, whether it be the post office recognizing postal codes or banks recognizing the digits that you write or those kinds of things. This is one of the early use cases of machine learning, actually. But if you think about how you might solve the problem today without machine learning, so if you would imagine, and I have imagined, writing a program that would recognize these digits, and I can tell you that it would be difficult for me to do that, and it would probably take me months, to recognize lines, vertical, horizontal, angled, loops, half loops, whether they're closed, how many loops am I seeing, and just kind of defining the different digits by these kind of components. I think it would just take a while to write it in a traditional way. But with machine learning, we're going to do it 2 or 3 times today, and you're going to see how quick it is and how effective machine learning is. And it's a very different approach to solving a problem like that, like this. So this is the problem that we're going to solve. And just a reminder on what machine learning is. I have 3 slides from my one-on-one class. You could think of machine learning maybe as a function finder. So you're trying to build an algorithm that takes features, they're called, but you might consider that X, and returns Y. So this is the data set that I used in the last class. This is the data set of flowers, and you have 4 features of each flower. And then you have the species of that flower, and machine learning essentially is used to train the the function that takes those features and then identifies the flower. So that's one way to think about machine learning as a function finder. So how do we take those pixel values and turn that into a digit 0 through 9 is essentially what we're trying to solve for. Actually, can somebody mute the person that's not muted? Great. Another way to think about machine learning is in classical programming. Essentially, what we do is we interview subject matter experts. So that might be doctors, nurses, or lab techs, or bankers, or what have you. We listen to what they say, and then we codify those rules into thousands and thousands of lines of if-then logic. And then you have a program. a program where you've coded the rules in, you can feed it new data, and it'll give you answers. So that's the way we've been programming computers since the beginning of time. Machine learning is different. You don't do it that way. You let these generic algorithms, these generic machine learning algorithms, figure out the rules by giving it lots of data. So we're going to give it lots of digits, lots of pixel values and what digit it is. And the machine learning algorithm is a generic algorithm that will learn the rules. And then once you have those rules, which are embedded in a model, then you can run new images through it, and it'll give you the answers for those. So it's kind of a very different way to solve similar problems that you would with classical programming. And then maybe lastly, the algorithms I went through in ML 101 are these. There are weight-based models, of which neural networks is one of them. So we'll dive into that a lot. But there are other different kinds of models, tree-based models, clustering, kind of nearest neighbor type models as well. But we're going to deep dive into this neural network and deep learning concept. Okay, so let's talk about the data set that we will use to solve this problem. So we have 42,000 digits, basically, in our data set. Each digit is represented as a 28 by 28 grid of pixels, and then each pixel has a grayscale value. So the black pixels are 255, and the white pixels are 0, and then everything in between. So that 28 by 28 gives you essentially 784 features per instance. So each of these 784 pixel values are your features, and then your label, your Y, is whether that digit is a 0 through a 9, basically. Okay, so that is what the data set looks like, and this comes from a very famous public data set that was called MNIST. And it was created by basically getting students to handwrite a bunch of digits that they were told to write, basically, and then they saved this and used it to train ML algorithms. So it's been a very kind of famous and useful data set that's out there. Okay, so now we're going to go into our first exercise. So for the first exercise, what we're going to do is look at the data. What do these digits look like? What do the data sets look like for our little our data set? So you're going to click on the Kaggle link that we sent out. That's going to bring you to the digit recognizer competition. Then you're going to click this code link, and then you're going to click this new notebook button. And what this is going to do is provide you an environment in Kaggle called a Jupyter Notebook, basically, where we will do all of our work, basically. So it's an online version of the Jupyter Notebook environment that Kaggle provides. And Jupyter Notebooks, if you haven't used them before, are basically the coding environment for data scientists, at least the most popular one, and allows you to intermingle code in a kind of interpretive, interactive environment with the results of that code. So different visualizations and tables and things like that. And you'll get a feel for it as we go through this class. So we are in a Kaggle notebook. Now you see this button right here. This toggles back and forth the sidebar. So you can click it to move the sidebar out of the way so you have a little bit more room. So the first thing you're going to do is do File, Import, and then import Notebook 1 that we sent out. It should say Notebook 1 Data Exploration Start. So click Import, and that will give you kind of all you need to get started in this class. So I'll describe what's in it in a moment. But the way to run a cell, so these are called cells. The way to run one is you hit Shift, you click in it, and then you hit Shift Enter. Now this first cell takes a while to run because it's now creating the VM or container in Kaggle dedicated to you. So you can see it up here, draft session, waiting for Jupyter, and starting up that session. And also right here, you can see the stop sign kind of turning around. And when it's done, you'll see a number that shows in what order the cell was run. So this cell is run. It was run first, and it has this particular output. So it's printing the files that are available to notebooks inside this competition. Okay, so the next cell is the important one. So run that. So click in it and do Shift Enter again. This cell contains all the imports that you'll need for this class. It contains a show function, which I won't explain other than we'll use it. And this will show digits. So if you send it a bunch of digit pixel values, it's going to show them for you. So it's not really ML, so I'm not going to explain how it works, but it's actually pretty straightforward. And then a couple of variables which we'll use and some environmental things that make the class go better. Okay, so now we're going to load up our training data to take a look at it in this cell. So we're going to use the pandas library, which is the most very popular library in data science land. We're going to use a method called read_CSV, and then you're going to use this variable to get access to the data. So that brings you to a directory, and then add on the end train.csv. And that will go to donwoodlock.com, this folder, this file, and then load it up and show you the results. Okay? So I have a little bit of annoying coding style, which you'll see is that I often get an expression correct, and then I set a variable equal to the expression afterwards. So now what I'm doing is taking the results of that and putting it in this variable train df, and then showing train df. So this, and then I'm running it again. So that will do it again, unfortunately, but when I'm playing with things, it helps to do it that way. At least it helps me. So what we see is what's called a data frame. So the data frame is the main data structure for pandas. The equivalent, if you haven't used pandas before, is probably a SQL table. The main difference is, think of it as a SQL table with like 400 methods, and we'll use a bunch of those methods in this class. The table has 42,000 images in it, 42,000 rows, and each row has a label column. So this will be the number 0 through 9. What digit is this? And then it has the 783 pixel values, all of which look like 0, but we'll see that they're not all 0. So that's the 28 by 28 image. Okay. Now what we're going to do is pull out y and x from the pieces of this. So y equals train df label. So that's the way you pull out one single column and put it into a variable. And the way you pull out a bunch of columns is this. Actually, this is the easiest way in this case. So what this second line will do is create a new data frame by dropping the label column from the train df data frame. So that will create x and y. Okay. Now we're going to show a single digit from this. So I happen to know that the digit in the 10th index location is a good one. So that's the method that you use to pull that one out, the index location. And it does look like all zeros. So what I'm going to do is kind of reshape this. So the way I want to get it into a 28 by 28 form. The way you reshape something is you can pull it into a slightly different data structure, which is a NumPy array, which is another very popular data structure that's used under the hood in pandas. So that also looks bad, and then you can reshape that array to be what you'd like. So now we're making it a 28 by 28 array for one digit, and this doesn't look that great either. But if you put it into another data frame, just a data frame of rows and columns for that single digit, then you can start to get a feel for what that actually looks like. So you can see now you have the 28 rows, you have the 28 columns, and you have the pixel values. All the around the edges are 0, which is white, and then you can see the digit itself. And we can all see that that's an 8. And so pure black is 255, and you can see it becomes less than pure black as it transitions to white around the edges. So that looks cool. You can show it as an image instead of a data frame of pixel values using a different library, matplotlib. There's an image show function. Yep. Here you have to pass a 28 by 28 array. So I'm going to grab the argument to the data frame and pass it to image show, and that will show it. It has a funny coloring, so you can actually change that by saying cmap equals grays as a second argument to image show, and that's going to show that image in its usual recognizable form. Now let's show the first 25 digits, and we're going to use the show method that I referred to before. The show method, let's see, yeah, you can see it takes the x value, so it takes the pixel values, and then the indexes is the second argument. So we're going to show the first 25, and Python has a range function, which is basically a iterable that goes from 0 to 24 basically. So that will show the first 25 digits in the data set, so you can see what those looks like. Here's the 8, the 10th index value that we see above. Now let's take a look at the first instance of each digit, the first 0, the first 1, the first 2, that kind of thing. This is slightly tricky, but the way you can do it is y contains the digit values, the labels. There's a function of lists, so we're going to turn this into a list. So that's the same data as a Python list. And there's an index function, or index method, of a list to find the first, the index value of the first occurrence of a value in the list. So the first 6 in the list is at the index value 21, and you can see that right here. So what I'm going to do is generalize this by using this list composition thing, which is kind of a thing. It's a very nice feature actually, but it's particular to Python. So we're going to say the index of n for n in range 10. What that does is it will loop through, it'll have n loop through this range, and then it will replace n in the list with the value of this expression. So that essentially has replaced the 0 through 9 with the index values of the first occurrence of 0 through 9. So that's so that gives you the index value. Now we can use our show function, use that as the second argument, and that will show you the first occurrence of 0 through 9. So sorry, that was a little tricky because Python has this, it's actually excellent little structure around this list composition, but if you haven't seen that before, it's a little unusual. And so here's what you see, the first occurrence of each of the 9 digits, and then we can also show the first 7s. Let's take a look at that. The way to do that is actually, you have y, if you recall. If you say y equals 7, it replaces, or it evaluates to a series of booleans, and the boolean will be true when the value equals 7 and false otherwise. So what you can actually do is turn that list of true falses into a list of indexes by doing this. So the NumPy library has a method or a function called where, and that gives you the index values of the trues, basically. So the first true is index value 6, and you can probably see that up here. Sixth index is indeed a 7. And it returns this. It returns a tuple with one value. So if you pull out the 0th index of the tuple, you get a real array. And then we just want to do the first 25 sevens. So that expression will will clip that array to just 25 elements. So these are the first 25 sevens, at least the index value. And now we can use our show method again to show the first 25 sevens. Again, the show method takes the array and then the index values that you want to show. So you can see now the first 25 sevens. And you can see, this is a nice reminder that people write sevens differently. Some people put a little cross in their 7, looks like a little over 10% of people. Some people use 2 lines to draw 7, 1, 2. Some people use 3, they put a little hat on it, 1, 2, 3. Some people have a very vertical line here, or not too angled. Some people have a heavily angled line. Like that one's almost vertical, that one's almost 45 degrees. And some people make mistakes, or the pen didn't work that well. So here you see a little blank there. So there's great variety in the way people write these digits. So it's quite a problem actually to solve, but we will solve it in this class. So now what we're going to do is, now that we've kind of explored the data set, hopefully. First of all, don't panic if you didn't finish. Actually, we give you can either continue to use that notebook if you're caught up, or there's kind of a new notebook that you can use at the beginning of the other exercises. So so if you didn't quite get it done, that'll be just fine. Okay, so we're going to use machine learning twice. Once using logistic regression, an algorithm called logistic regression, and the next is with neural networks and deep learning. So logistic regression is a building block to neural networks. So I thought and it's really a very basic ML algorithm, but I thought it would be good to start here for those reasons. So if you were part of my machine learning 101, the essence of logistic regression is linear separation. And so as a reminder here, we're looking at a graph of 2 features. It's that flower database, the sepal length or sepal, I'm not sure, and the petal length. And then there are 2 kinds of flowers in this graph, at least, the blue X's and the red squares. And you can see that based on these 2 features, they separate themselves in this linear space. And machine learning just searches for that line, basically, that separates the two classes. And so the function that linear separation uses is basically just a line. And the line is constructed by having a weight multiplied by each feature, and then a weight at the end, and that basically makes a linear equation, and things that are on one side of that equation. So if that equation is greater than 0, let's say, it goes to one flower, and if it's less than 0, it goes to another flower. So it's a pretty straightforward equation. You can see it in the parentheses here. Now flipping to our digits example, it's the same thing. You just can't graph it on a 2-dimensional display like that. It's 784 dimensions essentially, but the math is the same. It's a linear equation. You're hunting for the coefficients, which are called weights in machine learning, and then each coefficient basically is multiplied by a feature, and that becomes a linear equation. And in things greater than 2D space, it's not a line really, it's called a hyperplane, but it's basically searching the space to separate out the different classes. Now there's two additional things that are thrown into the math here. One is that it turns this into a probability. So instead of, let's say, instead of a machine learning algorithm that's going to predict whether it's going to rain tomorrow or not, you could turn that into whether the probability that it's going to rain. And the way that works is it's a function called the sigmoid function, and it's graphed on the right side of this slide. And very positive numbers become 1 or very close to 1 in the sigmoid function. Very negative numbers turn into 0. So essentially, you're looking at a number between 0 and 1, which is your probability. So on one side, there's 0% probability of something being part of a class, and then on the other side, it's a 100% probability, or a 1 in probability terms. And if it's right in the middle, it's a 50% probability. You can see in that equation, the 0 right in the middle is 0.5. So 1 is a sigmoid function is applied to this linear equation to turn that into a probability. And the second is because there are 10 digits versus something like, is it going to rain? Yes, no, versus a binary problem, that it actually builds 10 machine learning models under the covers. And when it's doing its prediction, it asks each model, what is the probability that this digit is a 3? And what's the probability that's a 4? And what's the probability that's a 5? And it kind of asks all 10 models that question, and it picks the one that has the highest probability, basically the one that's most confident that it is right. So that's how logistic regression basically works. Another way to draw it, I guess, or state it, which is useful when thinking about neural networks, is just turning the math kind of sideways. So you have your features on the left, and you can think of the feature values as being a value in each of those cells. Then you have the weights, and you can think of the weights as the connecting lines in this graph. And then that cell where it says predict, that one in the middle, is essentially what's called a dot product. So the multiplication of each feature by each weight and then added together. That's called a dot product. So you take the dot product of the features and weights, and then you squash it with that sigmoid function. So you take very negative to very positive and squash it to be 0 to 1. And then you compare that with the target, which are 0 to 1. So if you were training the machine learning model for the sevens, the digit 7, then each digit is either 7 or it's not. So the target is either 1 if it's a 7, meaning it's a 100% chance it's a 7, or it's a 0 if it's not a 7. And essentially, you make a prediction, a probability, you compare it with the target, and then based on how far off you are, you adjust the weights slightly in the direction of being right. So that's the essence of the training process. And I describe it, I'll describe it a little bit more in a moment. So, but let's build a little bit of intuition on the weights. So here's your equation of the probability that this digit is a 7. You're taking each pixel value, you're multiplying it by a bunch of weights. Let's assume this model has already been trained, so you already have a bunch of weights. And then you squash it with the sigmoid function to be a number between 0 and 1. What does a weight of 0 mean? What 0 essentially would mean is that the value of X, the value of that particular pixel, does not matter at all. Whether it's white or black or gray or everything in between, it doesn't seem to have any impact on the digit's value. Okay, so we would expect the pixels on the outside of these images to all have weights of 0 because they don't really matter. I mean, generally speaking, they're all 0. The pixel value is 0, but they're also going to have a weight of 0 because they just don't influence what digit it is. So that's what a weight of 0 would mean. If the weight is very positive, what that essentially means is that this digit likes that pixel to be black because the black is the higher pixel value, and then multiplied by a positive weight, meaning we kind of like that to be black. So for sevens, you could think of the the kind of top row, or at least if you move it down a little bit, kind of if you move down a third, let's say the top horizontal row, it likes that to be black in a 7. Certainly likes the top right corner to be black. It likes pixel values here to be black. It probably doesn't like pixels on the left middle to be black, or the bottom right, or those kinds of thing. So it's kind of those weights are looking for black pixels. And if you have a very negative weight, a big negative number, it means it does not like it to be black. Basically, it kind of reduces the probability when it sees a black pixel. So it would be just the opposite here. It's the pixels that it likes to be white for a particular image. So for instance, the digit 0, of course, it likes the pixels in the middle to be white, and it likes the corners to be white. So that's what will happen as the result of the training process. It's going to generate a bunch of weights that help it be as accurate as possible based on whether the digit really likes white or black in that pixel position. Okay, hope that makes sense. And then just a touch more math on this thing. You can think if you think back to that you know, that yellow and white thing that that picture there on the top right. If you think back to that thing, that basically when you're comparing the prediction with the target, you can calculate a loss. You can calculate kind of the error, the total error. So the way logistic regression works actually, in a lot of these models, is they randomly select weights to start. So just some random number, basically, they set for each of the weights. And then they go through all the data and make predictions and then calculate the total error. And in that, and we want to minimize the total error, right? So we want values for the weights that minimize the total error. So you could think of this as a minimization equation if you think back to calculus. So the error, the total error value, is a function of each weight in a sense. So if the weight is too far to the right, then the error will be greater. If it's too far to the left, the error will be greater as well. So you kind of want the bottom of the hill for the weight. And that's the way the algorithm basically trains itself. It builds an equation that an error is the function of each weight. When you make a prediction, what it does is it will look at the slope of that error. And the reason it looks at the slope is if the slope is positive, it knows the weight needs to move to the left. And if the slope is negative, the weight needs to move to the right. If the slope is large and positive, it has to move a lot to the left. But if it's small and positive, it's kind of down here. It's just going to move a little bit to the left. So you're basically using the first derivative of the error function as a function of each weight to figure out how much to adjust the weights after each training round. So, so it's actually using the calculus you probably have forgotten to do this algorithm, believe it or not. And just in 2 dimensions, the first derivative is called slope, as you probably all recall. But in n dimensions, this is actually called the gradient. And this whole algorithm is called gradient descent because you're descending down the hill, basically using the gradients based on where your prediction is. So that might be a little bit too much detail and too much math, but that's essentially the way machine learning works. Is it's running through data, calculating errors, and then nudging the weights down the hill to try and find the minimal value for those. Okay, so that's the quick explanation of logistic regression. Now we will do our second exercise where you will train the model based on the logistic regression algorithm. And as I mentioned earlier, you can use the same notebook if it's all in good shape. If it's not, you can import notebook number 2 based on the links we sent out earlier and start the exercise from that notebook. Okay, and then lastly, Melis should have posted the time that we'll all see you back again. So good luck with logistic regression. Okay, next what we will do is build a logistic regression model to try and predict the digits from these pixel values. So you can start with the notebook that you left, provided you're caught up and everything was working. Otherwise, we provided you another notebook to get started. So you're gonna have to go back to where we set x. A lot of these, and what we want to do is normalize the pixel value to be closer to 0. A lot of these machine learning models are optimized to deal with numeric feature data that's close to 0. Right now our features go from 0 to 255. So if you just divide x, or just divide this expression by 255, it'll work out better for these models. Okay, it's not impossible to deal with larger features, but it works out a little bit better. So be sure and run that cell again. So make that change, hit Shift Enter. You don't actually have to worry about these other cells. Okay, now you're going to go to the cell that says split x and y into training and evaluation data. So what we're going to do, when you train a machine learning model, to figure out how accurate it is, you have to set aside some data, which is called evaluation data, and not train on that data. So you can really tell how the model does with unseen data, it's called. And the way we do that is there's a very popular function of a library called the train test split. And what it does, it takes x and y, basically, and then it splits it into these two parts. And there's a few other parameters that I like. One is to set a seed. I would prefer that all of you get the same results in this class, so I have a seed that I'd like you to pass. And then the test size, let's do 20%. So that means that if you hit this, actually it's hard to read the results of this, but that means 80% of the data will be used for training and 20% for evaluation. So the variables that we're going to use are x train, x eval, y train, y eval. So we're going to take that and set that into these four variables. So it's going to take x and split it into 80%, 20%, and it's going to take y and take the exact same rows and split it into the train and evaluation set. And just test that I got everything right. You can look at the shape of x train and the shape of x eval and make sure it looks okay. And so it does. So what this is saying is that 33,600 rows went into x train, 784 columns, which is good. And then 8,400 rows went into x eval. So that's going to be our evaluation set, 20% of the data, and then our training set is the 80%. So now skip this next one. We'll use that later. And go to the create model statement. So what we're going to do is the model equals logistic regression. And the only argument that we're going to use is to set random state again, so you get a same model, hopefully the same model as I got. Okay, so that statement creates a logistic regression model. It doesn't train it yet or anything like that, and plops it in this variable model. Okay, so now we're going to train it, and that is the fit method of that model. So what you're going to pass is x train and y train, and then hit Shift Enter. And what that'll do, this takes about 10 seconds, so don't panic. What that will do is take the training data and basically build, do all the logic we've talked about. Have some kind of algorithm, some level of weights, essentially, that take the pixel values of the training data and translate that into a probability that it's a particular digit. Okay, so that's the fit method, and then the other key method is called predict. And then in here we're going to predict on the evaluation data. You don't need to pass y because it's just doing the predictions. And so you can see it's predicting, numbers from 0 to 9, basically. So it's predicting that first thing is a 4, the next one is a 4, the next one is a 1, that kind of thing. So we'll see how accurate it is. So stick the results of that expression into this variable preds for the predictions so we can use it in a moment. And let's show the accuracy. So what you can do, actually let's just eyeball it. So if you look at y of l, you can see 441 is the same, 441, and then at the end 800 is the same, 800. So it's looking pretty good. But if you want to calculate an actual score, there's a tiny little method for that called accuracy score that I imported. You pass in the true values, which is in y of l, and then your predictions, which is in preds, and then you get an accuracy score. So this is 91.6% accurate, which is great. I think that would be better than if I hand wrote the function for sure, and we didn't really put a lot of work into this quite yet. So now you can actually show, you can use my show method to show the first 25 digits and how it did. So the way to do that is, instead of showing x, do show x of l, because we're just talking about the evaluation. Set, we're going to show the first 25 there. And then there are two other arguments, which I didn't really tell you about, but I will now. One is if you pass in the true data and then you pass in your predictions, it will put those two values on top of this display. Okay, so now you can take a look at how well it did. So let's take a look. Okay, so it got the first row right. The second row, it thought this was a 2. And to me, it does not look like a 2. I guess it's got a loop on the top. It's got a line on the bottom. It's got a curve going on, at least in the beginning. But otherwise, you know, it's not really a 2. But it did okay. Everything else it got correct, which is lovely. So it got one wrong out of the first 25, which you know, you would assume with this accuracy score it would get about 2 wrong. So that's pretty good. And then you can also look at the ones where it got wrong, the index values. So if you do y of l does not equal the predicts, you're going to get this this true-false array, and true means that it got it wrong. So what we're going to do is do the same thing we did before. Use the numpy's where function. This is going to give you the index values of where it got wrong. So it got the 6th one wrong, which is that one right there. And then the next one it got wrong is 35, and then 39. You can see here it gets every 20 or 10 wrong. And for 8400, it should get about 840 wrong, basically. So we got a full page of things that got wrong. So 91.5% is pretty good, but I think we can get better. So what you should have seen with logistic regression is getting to a 91.5% accuracy, which I think is very good. And again, if I were to write a program to do this by hand, I bet you I would not get that. I should try it someday, actually, but I bet you I would not get anywhere near 91.5% accuracy. So that's pretty good for, you know, kind of a beginning algorithm for machine learning. And as you saw, of the 25, the first digits, it only got 1 wrong. So you would expect with that accuracy, it would get 1 or 2 wrong, probably 2 wrong, 2.5 wrong, essentially each 25 digits. So that was off to a good start. But you can tell it's a 3. You know, it kind of should have got that right. It's maybe not the most normal 3, but nevertheless. So now what we're going to actually, and then the other recap is this, which is the list of what it got wrong. You can see it got a bunch wrong for 8400, probably got you know, 800 wrong basically on that. So a nice big list. So I bet we can do better. And so now we're going to move into neural networks, and I'm going to turn it over to Marta to teach you this piece of the class. So I'm going to stop sharing and why don't you take it over, Marta?
Absolutely. So you should be able to see my screen soon. It says deep learning.
Yep.
And we are going to have a deep learning exercise. But before we get into that, I would actually like to talk a little bit about the history of machine learning, because you'll find out that the various techniques that we'll be using today are really built on each other. And understanding how this development happened will help you understand the techniques themselves. And the example that we're going to be using today is university acceptance. You can wonder, could we predict whether a student can get into a certain university based on their SAT score and based on their school grades? And this data is somehow correlated. The higher the SAT score is, the higher the chances of admissions are. And a naive interpretation of university acceptance will be plotting a graph like the one you see here on the left, where students that have lower school grades and SAT scores don't get in, the ones who have a higher score get in, and we can divide the two cohorts with a straight line and find what the equation of this line is according to our best guess. Well, the first machine learning algorithm was called perceptron, and it worked just like this. So what it would do is it would work pretty much like a neuron in our brain works. It would find the equation of a line, and then it would pass out a binary answer, a yes or no answer, which is why it was called a binary classifier. And this, in a way, is what an artificial neuron does. It's the most basic form of machine learning. What you just did with linear regression was actually a step further from this. Perceptron is very, very old. It was invented in the 40s, and it actually took a whole 15 years, believe it or not, for it to be implemented, even though it's such a basic concept. And it did something that was very similar to what we're doing. It was an image classifier, it did image recognition, but it could only recognize images that were 20 pixels by 20 pixels large. And today, clearly, we have more computational power, but we also have models that are a bit more complicated and a little bit more helpful. And logistic regression, which looks similar to what perceptron is, because again, it is a linear classifier, is a bit more advanced because it's no longer a binary classifier. Earlier, Don told you about the sigmoid function, which is taking the output of our classifier and returning a probability. And that's exactly what linear regression, the algorithm you just used, does. It finds a linear function, and then based on how far away your data point is from that linear function, it finds a probability for the status of that point. So any point that is very close to the separator line will have about a 50% chance of being in either category. But the further away you get from the line, the more your probability increases or decreases. And this is helpful when you have a problem like recognizing a digit where you have 10 possible answers from 0 to 9, and you want to pick the answer in which you have the highest confidence, and therefore the answer with the highest probability. Now, can we take this a step further? What happens if you have a graph like this? So let's say that only students who have both very high SAT scores and very high school grades are accepted. Well, if you look at this, you'll notice that it is hard to divide this data set with a linear classifier. And there are a couple of workarounds. One workaround would be looking at different features, saying, okay, if SAT scores don't give us a very definitive answer, Could we look at extracurricular activity engagement and change the parameters that we are plotting on each line? But sometimes this just isn't possible. And when it comes to recognizing images, really the only features we know are the color of each pixel. And it's not really intuitive how we should plot these images in a multidimensional space. And so, could we find a way to classify this data set with a separator that is not linear? Well, yes, there is a way. And for a matter of convenience, could we use the knowledge that we already have about linear models, such as with linear regression, to create a model that is nonlinear? Sure enough, we can. What happens is that if we can develop two separate linear regression algorithms or two separate linear regression models, we can then combine them to create a third model that is nonlinear. And if you look at these graphs, they're not really drawn at random. You can see that this line plus this line in the way they separate space combine into something that kind of looks like this area in the upper right corner. And this technology is called a neural network. And this is how it works. We start with an individual linear separator, like the ones we just saw. And then we feed our features into the linear separator. And to its output, we apply a function that is called ReLU. And you can think of ReLU in these terms. If the output of our equation is negative, we return 0. And if it's positive, we just return the number itself. And ReLU was developed in the 60s, and it's a very, very simple function, but it has one important feature. It's the fact that it is nonlinear. This you can see here, it has a corner, like a non-differentiable point. So it introduces nonlinearity into our system. It's a very simple twist, but it is what allows us to combine multiple linear models. And we can go ahead and create a separate linear model, apply ReLU to that model as well. ReLU is this function. And then we take the output of the two linear regression models we have, and we combine them into a third linear model. And to that third linear model, we then apply the sigmoid function to obtain a probability output. And these two models we see here that don't actually make it to the final output are called the hidden layer. And a hidden layer is what makes neural networks so special. Another way of visualizing the same exact model we look at is this. So here we have our features. This is all the data we know about a certain image. And we feed our entire set of features into multiple linear models. We apply ReLU to each of them. And then we combine that into a new nonlinear model and apply the sigmoid. That's exactly what we saw in the previous slide, so there is no news here, but I wanted to introduce this view because we will be using this more compact view a lot throughout this presentation, and it's good to become more familiar with it. And once again, this is our hidden layer, and this is our final layer. So can we take a step further? What happens if we find a system for which a single hidden layer isn't enough? Well, we can actually put in as many hidden layers as we want. And for each of these hidden layers, we can have as many parallel models as we want. Here, there are 2 hidden layers, for example, and each hidden layer has 2 models. And this is called a deep neural network because it has more than 1 hidden layer. It's a lot of terminology, but you can really see how this builds onto linear regression. It's, pretty visual. All right. So what you can wonder is, how are we going to find the weights for each of these connections? As our system gets more and more complicated, finding the weight, which is the multiplier for each link, is going to become harder. Well, that's not really the case. It is computationally harder, but the theory is the same, because we, as Don explained before, we tuned our weights based on the error that our prediction had generated. And here we're going to do the same. We are going to take our features, feed them into the model, and then we're going to see what our prediction is. We're going to compare it to the known answer that we already have, because this is our training set. We already know the answers. We are going to take the difference between the two values, and that will give us our error. And we can propagate that back with gradient descent, which Don already introduced. And this method is called back propagation. It just means that we go backwards and we adjust the weights of each of these links to reduce our error a little bit. And then we send our features back into the model, calculate our new error, adjust the weights back. And we do this over and over and over again until we have sufficiently minimized our error. This is all based on the chain rule in calculus. That's why it works. However, if your calculus is a bit rusty and you don't remember the chain rule right now, that is definitely okay, because it turns out that we have a lot of packages that will just do the work for us. They won't just do backpropagation for us, they'll actually implement the entire algorithm. We just have to tell them how many hidden layers we want, how many models in each hidden layer, which activation functions we want to use, whether they're ReLU or the sigmoid function, and they will apply it for us. The two most popular packages are called TensorFlow and PyTorch. TensorFlow is developed by Google. PyTorch is developed by a team at Facebook, and they came out in between 2015 and 2016. They are the two most popular solutions. What we will be using today is Keras. Keras is just a Python API for TensorFlow. So it will allow us to use effectively TensorFlow in our Jupyter Notebook setup. And the neural network that we're going to build looks like this. We're going to start with 784 features, which correspond to each of our pixels. And we are going to feed them into 128 separate parallel linear models, which will make up our hidden layer. And once we have those, we are going to feed them. We're going to feed each of these 128 models into our 10 probability predictions. So we will apply a sigmoid and come up with 10 predictions, one for each possible digit. And once we have these predictions, we are going to compare them with the known answers, because these known answers are going to be 0 for every digit except for the correct answer, which is going to be a 1 probability. We are going to compare a predicted probability with the correct answers. We are going to calculate the error, and we are going to feed that back into our model to minimize our error and tweak our weights. And we're going to do this for each image in our training set. All right, so with logistic regression, we got about a 91% accuracy. Can we do better using neural networks? We have a new exercise for you. If you are all caught up with the previous exercise, you can actually keep working with the Jupyter notebook that you already have on Kaggle. And if you got lost along the way, you can download Notebook 3 and import it into Kaggle, and that will get you set up to start right away with the third exercise.
All right. Now we are going to turn that logistic regression model into a neural network. So what you need to do, we're going to go back to the model cell where it says create model. So that's what we need to change. You can comment out that model, and that in Python you just stick a number sign in front of it, which is yeah, there's a keystroke for that, but that's okay. And now we're going to do that neural network. So what we're going to use is a function called sequential from the TensorFlow library, and this will be a sequential model, and that just means the model moves from left to right, and there are models that aren't sequential, which we won't cover here, but sequential models are the ones we're talking about. And then the layers are the first argument, a list of layers. So we have 2 layers. We have our 128 cell layer. It's called a dense layer when every cell from the layer to the left is connected to the next layer, which is not always true. We'll see in a little bit. But a dense layer is. So we're going to do a 128 cell layer. And you have to specify an activation function, which we're going to do relu. So that's layer 1. And then we have our last layer. And this will be the 10 probabilities, and the activation function will be soft max to determine those probabilities. So you can run that to make sure you don't get an error, but there's one more line to add there. So that creates the model, and then TensorFlow needs to compile the model before you do anything else with it. So there's a compile method as well, and the 2 parameters we'll be using are optimizer. And this is basically the way that the algorithm that it'll use for gradient descent. There are different optimization algorithms to make it faster, and we're going to use Atom, which is a different method or function that I imported. And then you need a loss function, which is how to evaluate the loss so you do the gradients correctly. And this is a little bit of a mouthful, but it's sparse, categorical, cross, entropy. Okay. And what that loss function does is it doesn't just evaluate whether you got the digit wrong, let's say. It penalizes you for lack of confidence. So if you got a digit right and you said you had 80% confidence that that's a 9, and it does turn out to be a 9, you'll get a bit of a loss versus if you were 99% confident that it's a 9. So it kind of looks at your probabilities, how close to 100% or 0, depending on whether you got it right or wrong, those probabilities are, and it sort of penalizes you for not being as confident. So it really tries, it's kind of a better loss algorithm to really train those weights properly. Okay, so that is the model. So run that cell again and make sure you don't get any errors. So we have defined our model, we have compiled it. Now we're going to train it. The training takes a few more parameters, the training of a TensorFlow model. One is how many times do you want to pass through the data, and that's called epochs. So we're going to do 30 epochs. And then what is the batch size? It's trained in batches, basically. So we're going to do a batch size of 75, actually. And you can also specify the evaluation set by using this parameter validation data. And then you can pass in a tuple, it's called, a list of, kind of like a list, but a tuple of your evaluation data set, X and Y. And it's not going to use that data for training, but it will use that for showing you how the training is going. So I'm going to hit Shift-Enter, and you will see the training starting. So you see that it's going to run 30 epochs, basically. They take a few seconds each. And the validation loss is basically the sparse categorical cross-entropy number. But most importantly, you want that number to be low. So you're kind of watching the training drive that down to 0. And what machine learning people will do is they'll take a look at this number to determine whether they should train for more epochs or train for less, or those kinds of things. So you can see I'm going to keep it 30 just for my own ease, but you can see that around 12 or 11 or so it kind of has bottomed out, and the rest of this is just kind of iterating around that same loss. Okay, so that is trained now. If you look at, if you make predictions now based on that model, the TensorFlow also has a predict method. You will see, it's taking a long time. Oh, it's still training? Okay, there we go. You will see that the format of predictions looks a little different. One is it seems like it's a multi-dimensional array, not a list of digit values. So one thing you typically will do is you will look at the shape of these arrays. Okay, so there's 8,400 digits, so that first dimension makes sense, and there's 10 values for each digit. And what these are the individual probability values for each row and each digit. Meaning, if I look at just one of them, let's look at the first one, we see 10 probability values. So it's kind of exposing the underlying probability values. And you could see most of them are very small. And this one is 0.99. So it thinks that there's a 99% chance that it's a 4. 0, 1, 2, 3, 4. Yep. And it's close to a 0% chance, but not entirely 0 for these other digits. So that's the structure of predictions that come out of TensorFlow. We need to turn that back into digits. So I'm going to describe how to do that. We essentially want to pick the index of the maximum value for each row. So the maximum value of this row is that, and the index of that is 4. So we want to replace basically this little array of 10 values for each row with the index of the maximum value. Well, believe it or not, there's a function for that in NumPy called argmax. And argmax takes an array, and it gives you the index of the maximum value. You can do actually I won't do it. You can do the maximum value of the whole array. You can do the maximum value of each row, the maximum value of each column. So we want the maximum value from a row point of view, which you would do by saying axis equals 1. So now you can see we kind of get what we want, which is an array of digits. Okay, so I haven't set it equal to preds yet, so change that line, say preds equals, and then show your preds. Okay, so now we have the format we like. You can go to the next cell and run it, and we have a 97.6% accuracy, which is great. So we went from 91 to 97.5 accuracy, which is really lovely. So let's take a look at the first 25 digits, which you can run again. Let's see how it did. First row is right. It got that 3 now. And it got everything else right. That's good. Okay, so it got everything right in the first 25. and you can get a better feel for what it's getting wrong in this cell. So run that one again. Looks like the first digit that it got wrong is 57, and then 74, 143. So you can kind of see maybe it's every 50 that it's getting wrong, or something like that. And you can see the total number it got wrong out of that 8,400 is a pretty tidy looking array. So it's not near as big as logistic regression, which is what you would expect from that higher accuracy number. But the question now is, can we do even better? So what you should have found, if you got all the way through that, was that the neural network now gets you up to 97.5% accuracy, which is really, really fantastic, and it does that pretty quickly, as you can tell. In our first 25 digits, it gets all of them right, even that 3 that logistic regression got wrong. And the total list of what's wrong out of the 8,400 that we set aside and didn't train on is much less. So we're looking at this 2.5% error rate. So whatever that is, 84 times 2 plus another half, so a couple hundred wrong, which is really really fantastic. So I wanted to just cover one topic real quick, and then we're going to train one more machine learning model. So why an activation function? We've kind of glossed over to some extent the sigmoid function, the ReLU function. You might wonder why we need these anyway. Well, it turns out that if you don't have an activation function, you don't have a nonlinear equation. And the best way to prove this is to just do the math out. And so what I did here is I built the world's smallest neural network. It has 2 features. It has 1 hidden layer with 2 cells, and then 1 final layer with 1 cell. And it has 8 weights, basically. That's what that neural network would have. So if you think about the equation for F, now it's just that linear equation, the weights times the 2 features plus a bonus weight at the end. And if you think about the equation for G, it's also a linear equation, right? Different weights, but the same 2 features. And then if you combine those together into a linear equation with H, so another weight times F and another weight times G, you get that equation. Now, if you take F and G and throw them into that, if you remember algebra, now you can see, I didn't actually go all the way through it, but you can see that the coefficient of x1, it's still going to be a linear equation. It's going to be, a bunch of weights kind of multiplied by each other, added together or whatever, but it's going to be some number multiplied by x1 and some other number multiplied by x2. So it's still a linear equation. So you can have the world's most complicated neural network, but if it's just linear combinations of linear equations over and over again, the end result is still a linear equation. You're still only going to solve problems that fit that linear separation space. But if you have some nonlinearity on F and on G, and then H we do for fun to turn it into a probability, but some linearity on each of those, nonlinearity on each of those cells, then you really have a network that calculates a nonlinear function, and it can map to the more complex spaces between the feature and the actual label. So the actual activation function is more of an advanced topic, why you pick one function or another, those kinds of things. But I just wanted to take a moment to kind of explain why these are actually very central to making neural networks work, as you have to introduce this non-linearity at some point in the flow. Okay, so we went from 91, we're at 97.5% accuracy. We got a half hour left or so. Can we do even better? So I said we would solve this twice, but we're actually going to solve it 3 times with what's called a convolutional neural network. And you can see that with a neural network, there are a lot of more kind of features or knobs you can turn. More layers, more cells, different activation functions. There's also different architectures. And so what Melis is going to take you through now is this architecture of a particular neural network that's very good at images. And so we'll learn about this neural network, we'll build one, and we'll see if we can get that accuracy even better. So I'll turn it over to you, Melis, to take us through that section.
Sure. Yeah, so I'll tell you about convolutional neural networks. Let me share my screen. Awesome. Can you see it now?
Yep, I can see it.
Great. Okay. So let's start by looking at why the fully connected network did not work well for our purposes. A fully connected network flattens the entire image into a single vector to make a prediction. So when we flatten a 2D image into a 1D vector, we lose all the information about how the pixels are relatively located to each other. But in reality, image pixels that are closer to each other are more related than those that are far apart. So fully connected networks do not leverage this knowledge. As an example, if we try to train our model using this image of a bike, our model would say, hey, okay, this first image is a bike, and I learned all these pixels as a bike. And when we test on the second image of the shuffled bike parts, it'll still classify it as a bike, which is definitely incorrect. So using this locational information is very important for our purposes. And one way to solve this problem is using local connectivity. And what this is we divide the image into little windows. And we can see that each window contains some part of the picture, which could give us more information about what makes an image what it is. So each hidden node is only connected to pixels in its own region and only tries to find patterns in that particular place. So for instance, if the first layer of hidden nodes are responsible for detecting, let's say, horizontal edges, it'll only look for horizontal edges in this particular region. So it might find, let's say, Einstein's tie, and this part might find a, strand of his hair. And each of these will collect some information about what it could mean. Then we can say that this use of parameters and sharing the parameters of the same image will let us actually classify the parameter weights and further reduce the number of parameters that we need to learn. So if we try to learn what a dog is, we will generate feature maps to use in our classification. And the feature map is just a collection of our filter results. So the filter grid will be extracting the features into a smaller layer until we have our desired result. And this is kind of like how our brain learns things. We look at small pieces of an image and then decide on what it is. So when we see a dog, we first see a dog's ears and then its tail and its legs. So the successive iterations of an image and extracting its features will tell us what it is. And CNN models are doing the same thing by extracting features. And using local connectivity and convolution, we are basically teaching our model to look deeper into one image and see more features. And I will show you what convolution is like. So spanning an image using a filter is actually called convolution. And to perform it, we need to have a filter. And filters are called kernels or feature detectors as well. And we will first take a window of our pixels from our input, and using a filter, we will multiply the corresponding values. So for this one, we will multiply 9 by 0, and the second one, we multiply 4 by 2, and 1 by 1, and so on and so forth. And then we will add all these numbers together, and then come to a sum of this cumulative image times filter. And then the sum of this outcome will be a single pixel in our output image. And this GIF also shows you how the convolution operation is done. So we're actually downsizing our image to a more simplified result each time. And these layers are used for different purposes sometimes. For instance, if you run a Gaussian filter across an image, you would get what's called a Gaussian blur. And that's because it averages the pixel values. And by default, the filters that we use in a convolutional layer are initialized with random weights. So the libraries like Keras and TensorFlow will be using random values. And that's how image filtering is done, so that we know that we're not learning just one feature. For instance, if we use the horizontal filter, we would only learn the horizontal features, which is not useful. But by using random weights, we can learn any feature that makes an image what it is. And then we will keep applying this operation until we're done spanning our image. And then we can look at how the convolutional layers work together. So our input layer is a single digit, like you see. So here we just have 7. And then we have a hidden layer that'll work through all of these and do the convolution operation. And then let's say it'll extract one feature. It could be horizontal edges or vertical edges. And these don't necessarily have to be edges. It can be any feature that indicates the 7-ness of our digit. So if we insert a dog picture, that could have been a feature for a dog's tail, its legs, or its color. And then it'll tell us the result, which is where the probability comes into play. It'll say, hey, this looks like the other 7s I saw, and it looks like a 7 from what I've seen before, because it has all these smaller pieces that I've seen. And like I mentioned before, weight sharing is an important concept here. It means that we use the same weights on our filters. So it could be any random weight, but when we span the image once, we just use the same thing all around the image. And objects are the same regardless of where they appear. So if you see a cat on the upper left corner, it is still going to be a cat in the bottom right corner. So it really doesn't matter where we look for the certain feature, but we can use the same filter everywhere else. And the advantage of this is learning less parameters and doing less operations. So it'll make our job much easier and much faster, basically. And architecture is something we have to decide. So if we say, hey, I want to go on with the CNN architecture, you can actually change it however you would like. And there are many ways to do this. Sorry. So we'll follow an architecture that uses a convolutional layer, a pooling layer, and the dropout layer. And I'll go through each one of these. So a pooling layer is used to summarize the results. And you could do max pooling or average pooling. And what this does is you take the maximum of each one of these results. So if you have 1, 1, 5, and 6, like in the red pixels, you will only take the 6 as a result. And then you can also do dropout, which will zero out some of the input and avoid overfitting. And what overfitting is, learning our training data too well. So in our case, it could be learning how to make 7 in one specific way. And we don't want it to learn just one person's handwriting. We want it to be able to recognize any kind of handwritten digits that'll be the same digit. So if we can make our model more agnostic to the data itself, but learn the patterns that's there, that's to our advantage. So using dropout and pooling will do that. And if we go back to how this architecture helps us, we can see that the image is processed as a whole image first, and it contains spatial information that we need. But at each step, we reduce the size of our image. So we first detect some of the features and then keep going smaller, and then we come to a conclusion of what it is. Then we can see that we don't have as many connections as a fully connected network. In each layer, we have the local connections that output the value depending on the previous few inputs from the previous iteration. So that means we do much less calculation compared to a fully connected network. And then at the very end, we will flatten our image and have a classification weight distribution, which is what Marta was also telling us about, that we will have a probability distribution saying it's one of the 10 digits, and it will be a 0 or 1 probability at the end that we compare it to. And this is what our CNN network will look like at the end, and Don can walk you through this part.
Yeah, sure. So
Yeah.
essentially, you just keep this. Oh, okay. I'll take
Oh,
this down.
sorry. I can share it again.
Yeah, why don't you do that? That'll be easiest.
Sure. Yeah, sure. How is it now?
Yeah, great. Okay, so in the exercise you're about to do, you'll build this network. And it's basically the way Malus described: a convolution layer, a pooling layer, then another convolution layer, and another pooling layer. And then we're going to flatten the data, and that'll make more sense in the video, and do kind of a normal neural network at the end with 1,024 cells, and then a dropout layer, which, as Malus described, will kind of randomly drop things so the model doesn't get too particular about particular images, and then the final 10 cells. So this will be the layer. This will be what you build in this exercise. And again, is the next slide that roadmap slide? So yeah, again, so if you're caught up, you can just use the notebook you've been using. Otherwise, you can import this notebook 4 to do the exercise. So go ahead and do that exercise. Malus will give you a time allotment here. And then we'll get back together and we'll wrap up just for a few minutes at the end. All right, good luck. Thanks. Okay, so now we're going to make this even better by making this a convolutional neural network. So let us scroll up. Actually, there's something we need to do with our data, the form of our data. So why don't you make it to the cell, it's after your 7s, the cell that says reshape X for CNN. So the shape of X right now, the shape of our data, is basically this 42,000 rows and 784 columns. Okay, but you recall for a CNN, it really needs to know which pixels are next to each other. It really has to see that in its two-dimensional form, not a single flat form. So we kind of have to give it in that shape. And what that means is that we want each image to have 28 rows and 28 columns. So we want to add another dimension to this array. And actually, we want to add a 4th dimension because most CNNs are used to working with color images. So the last dimension is the channel. So for each row and column, you usually have a value for R, G, B, and B. So RGB values. And for grayscale, we just have one value for the pixel, but we still want to have a dimension for that one value. The CNN will understand that the best. So you kind of want to have 4 dimensions: the digit, the row, the column, and then the channel. So the way to do that is, first of all, X right now is a pandas data frame. So you need to say X values. That makes the same data as extracts the same data as a NumPy array. So NumPy arrays have a reshape method. And here you can put in just the dimensions that you want. So we want 42,000 by 28 rows by 28 columns by 1 color channel. So that will evaluate to a 4-dimensional array. And it's a little bit hard to tell just by the way it displays. But what you want to do is take that and put that into the variable x2, and then do x2.shape to just check it. Okay, so now we can see that x2 has that shape. It's still 42,000 digits, but each digit is a 3-dimensional array, basically row by column by channel. So that's exactly what a CNN likes to see. So what you need to do next, now that we have an x2, is you see the first argument to train test split. So if you change that x to x2 and hit shift enter, now your training data is going to be of the form that you want, the 33,600 rows, but each image has its 3 dimensions, and then each of the evaluation images have their 3 dimensions. So that's step 1. Now we have data that the CNN likes. Secondly, this part isn't that important, but it's helpful when typing in the model to actually have a picture of the architecture in front of you. So I'm just going to drag it essentially from the PowerPoint into this notebook. So there's a display function, an image or display module, an image function from that, and then if you do URL to data plus cnn.jpg, this will grab the image from the from my website and show it, basically. Okay, so that's what we just saw in PowerPoint, and that's what we will create. And we will create it here. So what I'm going to do is comment this out. On a Mac, it's command slash. I'm sure it's something slash on a Windows machine, or you can just delete that stuff. So now we're going to do model equals. It's also a sequential model. You're also going to pass it a bunch of layers. So those brackets mean it's a list of layers. The first layer is a 2D convolution. So you're going to use this conv2D class, and we're going to pass in a number of parameters. Filters is the number of feature maps that we want, and there's 32 of those. You can kind of see that it's the third parameter here. So there's 32 different feature maps that we want in this first layer. Kernel size is basically how big of a window do we want to use as we're moving to the image. So we're going to use a 5 by 5 window. Now you may ask, why use 32? Why use 5 by 5? You know, it's just kind of a experience and momentum and whatever you used last time, plus a level of kind of tweaking and changing based on your data set. So there's a whole area of machine learning around hyperparameter optimization, and these are hyperparameters basically. And so you can do a process after you've kind of laid out your basic model to search for the best number of filters, or the best kernel size, or the best pooling size, or the best number of cells in some of these layers, how many convolution layers. All that stuff is up for grabs basically. So I'm just picking something for this class that works pretty well, but you can spend time, and typically ML people will spend time trying out different models, different architectures, different values for these different parameters, and to keep improving their accuracy. Okay, so the convolution layer needs the filters, the kernel size. There's something called padding. We're going to set padding equal to same. What that means is that basically, as it's windowing, when it gets to these pixels on the outside, it can't really do them because it has to read around those pixels. So padding means it's going to put a padding layer outside around the image essentially. And same basically means that I want an image as an output of the same size that I started with. So it's going to pad it enough to also do a 28 by 28 image. If it didn't pad it at all, this would be smaller, maybe 26 by 26, because it would lose the 2 based on that kernel size. Not positive, but same is very popular value for this, and give you the same size image. And then you need an activation layer, or an activation function for this layer, and we will use ReLU. Next we have a pooling layer, and you can pool by average, you can pool by maximum. This is basically going to pool by maximum, which was what was done in the slide. The default is a 2 by 2 little window, so it's basically going to take every group of four little pixel values from here, or cell values from there, and then just take the maximum. So that's actually going to shrink the size of the image to be 14 by 14, and there'll be 32 of them because it retains the separate feature maps. Then we're going to add another convolution layer and another pooling layer. So go ahead and copy this and just paste it. And the only difference is this particular convolution layer is going to have 64 filters. So we're going to look for more things as we progress here. So the first layer, again, might be looking for vertical lines, horizontal lines, that sort of thing. Here I might be looking for, oval circles or, kind of different higher level forms in the image. Okay, so we have two convolution pooling pairs. Now we're going to do a fully connected network, a fully connected layer of 1,024 cells. So the first thing you need to do is flatten your data. So now we're going to take each image from its three-dimensional form, which convolution and pooling layers like, and flatten it to the form that dense layers like. So that just flattens the data, doesn't do anything else to it. Now we're going to do a dense layer like we've seen before of 1,024 cells. And again, we'll use the ReLU activation function. We're going to do a dropout layer. And here we're going to drop out 50% of the cells. And essentially, this is from experience as well, building these networks. People found that these dropout layers really help the model not get too focused on any particular image, because you can't really trust that any image is there because of this randomness introduced into the training process. So it kind of forces the model to generalize based on what it's seeing and not overly read individual images or memorize individual images. So that's a dropout layer. That'll randomly drop out 50% of the cells in each kind of training batch. And then we have our final layer, a fully connected layer to predict our 10 probabilities. And for the probabilities, we want to use the softmax function. And that is the model. So now we're set. That worked. Go ahead and run it to make sure you don't get any errors. And now we need to compile it again. So I'm going to copy this down, uncomment it out, and there's one change we need to make. So the optimizer that works best, at least for this CNN and this data, is RMS prop. So we're going to change from the Atom optimizer to RMS prop. I'm not really going to explain why, other than it works better for this data, but these optimizers are more of an advanced topic, let's say. But essentially it's doing that gradient descent. It just does it in a different way. And then hit Shift Enter again. It has the same loss function, and make sure you compile your new model. The train is the same, so hit Shift Enter, and it'll start the training process. Now, one of the things you may notice is that it's running slower. So each epoch is taking more than 30 seconds, which isn't the longest time in machine learning terms, but it's a long time for this class, because 30 seconds times 30 epochs is going to be 15 minutes. And we do not have 15 minutes. So what I want you to do is go up here, click on this so you see the sidebar again. And you see where it says accelerator, do the drop down and hit GPU. And then turn on GPU. So what's going to happen is this is going to give you a new container, a new environment with a graphical processing unit as its compute CPU, basically. And the GPU can work much faster with matrix data. And libraries like TensorFlow can take advantage of a GPU if it sees it and run a whole lot faster, as we'll see in a moment. So the one downside when you make a switch like that is all your data is erased. So it's starting up a brand new, fresh container, even though it doesn't quite look that way. So you kind of have to run it from the top. So what we're going to do is you're still clicked in this cell. Go up here and do run before. Basically, this runs all the cells above that cell. So you can kind of scroll up and see these things are running again. You can scroll to the top. You can see these two cells have run. It's working on loading the data. It did it. It's working on showing images. It's done that. Reshape the data. Drag in this picture. Define the model. Okay, so now we're back here. So now if you hit Shift Enter in train model, the first epoch actually takes a little bit of startup time, I guess. TensorFlow's thinking about what it's about to do. But then it will go, I think it's about 2 seconds per epoch. You can go up here again and move out that sidebar so you can see it a little bit better. But now we're running at a pace that will train this model in 2 seconds times 30, so I guess about a minute. You can see the validation loss is a smaller number than the neural network, so that should translate into better accuracy. And I guess that's about it. I will stop talking for a few seconds while this finishes. Yeah, one of the, you can see kind of the loss was smallest around 12. Again, we saw that before. I really should go back and redo the whole thing with 12 epochs or something like that. But number of epochs is one of the parameters you would optimize. So a lot of ML is doing, trying these different model architectures, trying these different parameters, and number of epochs is certainly one of them. I'll just keep the 30 for ease right now, but you can try different values if you wish after the class. Okay, so now it's going to make the predictions. Predictions look good. Now if you go down to show accuracy, you run that cell again. Great. So now we're at 90, I guess 99% if you round it properly. So we've gone from 97.5 to 99%. Now you might not think of that as that much of an improvement, but the other way to think about it is number of errors. So we went from 2.5% errors down to 1% errors. So we've made kind of over a 2x improvement and driving that quite far down. So you really shouldn't do percentage of percentages because it gets a little deceiving because you can kind of write them in both ways. But this is a dramatic reduction in errors actually. So let's take a look at our first 25 digits. We'll run that again. Let's see, looks like I got everything right. Maybe we could try the next 25 digits. For this, you could do range from 25 to 50. Take a look at what that looks like. Looks like I got all those right. Maybe you can do the next 100 digits, so you can do 50 to 150. Don't enter too big of a value. I think my show function will croak if you do too big of a value. But I think 100 works. Obviously 25 works. Let's take a look at how it did on this next 100 digits. It's looking good, isn't it? So this is a very, very accurate model. It might have gotten something wrong, but I'm not actually seeing it. But the easiest way to tell is this next cell. So if you hit Shift Enter, you will see that it takes up until 196 to get one wrong. So that's really fantastic, and you can see it's a nice, tidy, small array of digits that it gets wrong. Maybe the last interesting thing is to take a look at the ones that it does get wrong. So this is the index values. Make sure you have this bracket 0 at the end. And then what you can do is show x of L. Copy that as the second argument. So this is an array of indexes. The third argument you do y of L. Fourth argument you do predicts. And you could see, oh, actually, Should have just done 10 of these. Well, we'll see. Oh yeah, it works. Okay. Actually, let me do 10. So see where it says bracket 0, just do another bracket, which is 0 through 10. So that's just going to take the first 10 values of that. Now it draws it a little bit bigger. So these are the first 10 that it got wrong. And you can see these are the more mangled digits. That's supposed to be a 7. That's supposed to be a 6. That's supposed to be an 8. You can see that that's supposed to be a 9, but you can see how the model would think it's a 4. You can see how this has a lot in common with a 6. That looks like they just were drawing a person with an eye there. You can see that these are the more, as you would expect, I guess, the more mangled digits that it's getting wrong. So this is fantastic. Getting the 99% accuracy, really, taking advantage of the latest and greatest machine learning approaches with the CNN. And you could even go farther. Hyperparameter optimize these things, add some more layers, add some more cells, really work it, which is what ML people will do to try and get the accuracy up to what the use case really demands. Welcome back. I realize now we're at the end of our 2 hours, so I'll just try and close in 3 or 4 minutes if you have the time. Otherwise, you could watch later, or I think you've got the main material anyway. But I thought I would just share some use cases for using what you've learned. So image recognition is probably the most successful area of machine learning so far. Machine learning is going to go a long way in our future, I think. But so far, it's done a great job with image recognition. And that's where you see impacts in medical imaging, self-driving cars, the Face ID, security, the way you open your phone, manufacturing, defect detection, smart cities, street lights looking for parking spaces, content moderation, making sure images posted on different social media sites are appropriate for those sites, retail. I mean, it's been used security, even human trafficking, helping our authorities combat that. So it's been really successful, and there's a lot of great use cases. But Melis was involved in some research projects that I thought were quite interesting. So I wanted her to share one of her projects, and then we'll be done. Melis, you want to talk about this?
Sure. Yeah. So I was working on a visual prosthesis project while I was an undergrad at Brown University. And this project consisted of a 3D printed glasses module for blind people, and it helped them navigate using a variety of sensors. So it was connected to a Jetson TX2 computer, and it has an earpiece. And this module can perform real-time object recognition, face recognition, hand gesture recognition, navigation, color detection, and obstacle detection. And I worked on the object recognition, which meant that if switched to that mode where the users can recognize objects, they could point out to an object and it would tell them what it is. Or there was a find my items mode where they could say, where are my keys? And the glasses would tell you how to find your keys. And the obstacle detection is when the users are walking, it would tell them where there's an obstacle in front of them and how close it is. So this project was tested with real visually impaired veterans at the VA hospitals in Providence, Rhode Island, and it had great feedback. And even developing this real time, we learned so much about how data sets should be tailored towards our purposes. And we were using a COCO data set, which is the standard, generally used. I think it's the biggest object recognition data set that currently exists. and it has all sorts of images. So it even has like animals like giraffes and penguins, which blind people may not see every day in their day-to-day life. So we decided to alter this data set to make it more suitable for everyday use. But yeah, I was very happy to work on this project, and the clinical test trials went really well. So it shows the great potential that visual deep learning and face recognition and object recognition have in real life.
Great, awesome. Yeah, that was a great project. And I will also note that not all machine learning is solving world peace. This is there's a lot of kind of fun machine learning oriented projects. This is one model that actually came out recently where you can actually type in text. You could see some of the text: teddy bear swimming in an Olympic pool, and it will draw an image from that text. And it has been trained on doing the opposite, getting images, getting their captions, and drawing a connection between the pixels and the text, and it can kind of do it in the opposite direction as well, which is really, really kind of funny. So at any rate, I will close by just kind of reinforcing how important machine learning is to our future. And I'll just leave it to some of our industry experts on this. The CEO of Google, has said that AI is probably the most important thing humanity has ever worked on. He's also called it more important than fire or electricity to humanity. So that's a certain amount of enthusiasm there. In our healthcare industry, Northwell, Michael Dowling, the CEO of Northwell, is basically betting on AI as a disruptive technology for healthcare. And then you see, I think it's blocking the name. Oh yeah, Fei Li from Stanford. She is kind of comparing it to the evolution of species when we developed eyesight in the animal kingdom, and AI technology really being on the verge of doing something similar, changing how we live, work, communicate, shape our environment, and all those sorts of things. So that's it. I'll thank you for your time and your interest in machine learning. We're certainly happy to get feedback on the class because we do it periodically, or any follow-up questions or guidance that you might need. But other than that, thanks for your attention. I hope this was interesting and educational and fruitful for you. And that's it. So have a good day, everyone. Bye-bye.